Let me to share the screens. Is it visible to all?
Yes,
Ashutosh?
sir. Yes, sir.
Okay.
It is visible.
Yes, sir.
Let me to stop my video. Okay. Okay. Good afternoon to all. So today's presentation topic is graph-based clustering. So hopefully many of you have fair bit of idea about graph clustering or basically the clustering. So I'll cover the basics of graphs if you do not know it. But hopefully I understand that you know the basics of unsupervised learning or mainly clustering. Uh, so what is basically clustering? Any example, many real life applications exist where we can see the applications of data clustering. So it's an unsupervised learning technique. I give this example always to introduce clustering. Suppose when flying over a city, unknown city, you are visited, let's say first time to the city, and you are flying and about to land in the city. So you can easily identify the different areas in the city by looking from the top. For example, which one is the forest land, commercial places, if there is farmland, river beds, mountains, etc. based on their features without any explicit training, because you are, so let's say, first time visiting the city, you do not know the topological distribution of the city, but still you can able to identify all these. So that is one example of unsupervised learning where you were not trained, but from your inherent nature you can still able to identify different parts of the city. So mathematically, what is cluster analysis? Suppose here the example is in a two-dimensional points, groups of points are given, and how to identify such groups so that two optimization criteria is satisfied. Right, so we have three different groups here, which is clearly visible, and how to identify them. If such points, data points are given in a n-dimensional space, so how to identify three groups or how many groups are there, how to identify them. So one of the criteria should be when you form the groups or clusters, they should be coherent, right? So data points within a cluster should be as close to each other, right? So that is called intra-cluster distances should be minimized. That means the similarity between data points within a cluster should be as more as possible. And the second optimization criteria is when you are considering the similarity between data points uh, in two different clusters, then the inter-cluster distances or dissimilarity should also be maximized. That means if some data points is here in the blue cluster and one in the, let's say, pink color cluster, then the distance should be as more as possible. So this is called separation. So these two are the basic optimization criteria. However, in clustering, even finding two best, if there exist only two clusters, and identifying the best two clusters among n data points is a challenge. It's a NP hard problem. Therefore, we do not have a definite algorithm, a single method by which we can able to identify the best clusters which lie in the data. What are the applications? For example, one of the applications of clustering can be a retail company may collect the following information on different household in their locality. Maybe the household income, the size, the number of persons in each and every family, occupations of the household's head, distance from nearest urban area, and can be many more data. Such data can be collected, and then they, based on the all these informations, they can categorize the different families into 4 different clusters. There can be many ways this categorization can be done. For example, cluster 1 can contain all the households which are small in size and they are high spenders, and maybe another set of families which are larger families and they also are high spenders, they can spend a lot of money to buy. Then there can be another set of families which are small family and low spenders and so on. Then once this is done, what the company can do, they can say personalized advertisements or sales letters, recommendation to each household based on how likely they are to respond to specific type of advertisement, right? So if you want to let's say sell a product, for example a LED television, let's say, then which family can afford, right? Obviously if it is a high cost, then you will definitely show the recommendation to cluster 1 and cluster 2 people, and if it is of low cost, probably will recommend that to group 3 or group 4 families. So this way lot of insight can be drawn. Then document clustering is a very popular. Here the goal is to find groups of documents that are similar to each other based on the important terms appearing in them. For example, if it is sports related news items, it can be, the documents can be related to entertainment, documents can be related to economics and so on. It can be political also. So based on some of the important words exist in the document, can you able to categorize them? For example, if crickets or hockey or tennis exist frequently, this kind of terms are in the data in the document, probably you will categorize them as news articles related to sports. Then the approach will be to identify frequently occurring terms in each document, form a similar measure based on the frequencies of different terms, right? Then you can use those frequencies, term frequencies we say, to cluster the data to find different news items. So if you see suppose in your smartphone or in your browser, if you use you are interested, let's say, for sports related items, news articles, and you read frequently sports related articles, so after few days you will see many suggestions related to sports only. So how do they know which articles are related to sports, so that they can recommend such articles to you, right? So that is one of the applications of clustering. Then summarization, this can reduce the size of large data sets. It has a lot of applications where the huge data processing them can be a challenge in many of the real life applications. So in order to reduce the size of the data, you can summarize the data, right? So let's say a document can be represented using few terms only, like the very important terms, or image can be represented using only few segments, so other segments are irrelevant. So that is called data summarization. So clustering is almost everywhere. This is one of the most utilized data mining techniques exist. Almost everywhere, every application you find clustering applications. So what is not clustering? So grouping them without using the class label may not be always called clustering. For example, simple segmentation of the students, let's say divide the students into different registration groups alphabetically by last name, right? So suppose say which set of students name starts from A, set of students starts from B, C, and so on. So you can simple segment the students. So that is not an example of clustering. So results of a query, groupings are results of an external specification. For example, you can specify how many persons are there whose income is greater than 5,000. So that is not, again, it can categorize the data into different segments. You can have range queries also, where you can classify how many persons are there whose income is less than let's say 10k, how many persons are there whose annual income is greater than 50, less than 50k, and how many persons are there whose annual income is greater than 1 lakhs, and so on. So that is not example of clustering. Then all other supervised classifications where the class labels are known are also not examples of clustering. So why this clustering is a challenge? Why do we study clustering? So suppose given set of data points where class labels are not known to you, so unknown data, suppose it's only two-dimensional data points given here which you can visualize. Then now if I ask you how many clusters are there, so how do you find the clusters? So from the visual perception, somebody can tell that this contains two different clusters. So here they are marked in two different colors. So that can be one of the scenario. So other scenario can be another person can identify, no, instead of two, this actually contains 6 different clusters. So all these 6 different clusters are represented using different symbols. And then another person can say, no, this is actually 4 clusters instead of 2 or 6, right? Then which one is the best way to represent, which one is the best clusters, how to find them? So this clustering is highly ambiguous in nature. You do not have a perfect example or perfect algorithm to identify the exact clusters which will work for all kind of data. So data can have different shapes, the cluster can have different shapes, they are of higher dimensional data. Then it can contains number of clusters can be huge, number of clusters can be less, the number of data points can be huge, it can be large data sets having millions of data points. So number of clusters or the clusters inside them can vary in shape, they can vary in size. For example, one cluster size can be very pretty big, cluster size can be pretty small, and so on. So therefore, identifying them is always a challenge. Am I audible properly, Asutosh?
Yes, sir, you are audible.
Okay, thanks. So you can interrupt me if I am not audible at any point.
Okay.
So here the clustering algorithm, the clustering technique, it's very challenging because you do not have the class of the data available. The label the which class they belong is not available at all. We assume that the data is unknown, and how to identify the inherent clusters within them, right? So there are many factors which influence the clustering technique. So first and the most prominent one is the clustering algorithm. So there are different clustering algorithms, clustering techniques exist. The partitional clustering algorithm, hierarchical, density based, graph based, and many more. So they can influence where you give your data as input, and sometimes some more parameters as given as input. For example, number of clusters are also given as input, and then the algorithm can produce the clusters within them. Then another prominent factor which influences the clustering algorithm is called proximity function, or we call similarity or dissimilarity, right? So what is similarity? How similar two data objects are. So dissimilarity is just the opposite of similarity, how dissimilar two data objects are, right? So we say how two persons' characters match with each other, right? So many times we say my friends are of similar character to me. How do we decide which two persons are similar? How do we decide the similarity between them? So you say two documents are almost similar. So of all of you, if you have done any kind of plagiarism check using any software, so there we say similarity checking, right? So you submit a software in any of the portal, then they can have a matching with different documents and say the similarity score of the documents is 32%, let's say. That means 30% of the content of your document matches with some other document. So it's a similarity matching. So how do you find that two objects are similar or two objects are dissimilar? So that plays a very important role in the clustering process. Then the quality of the clustering. So once the clusters are formed, then which there are two optimization criteria. I told you in the first slide. One is called intercluster distances. That means the data points within a cluster should be their similarity should be maximized. So that is called intracluster similarity. It should be maximized. That means this is also called coherent clusters. The data points within a cluster should be as close to each other, as similar to each other. And what is the second optimization criteria? The data points which are in two different clusters should be as dissimilar to each other, right? The quality of a clustering results depends on the clustering technique, the distance function that is used, and the applications domain. So I'll just give one simple example of proximity measure. There are many proximity measures. So the theme of the talk is not proximity measure. That's why I'll give the flavor of what is called proximity or similarity or dissimilarity matrix. I have chosen this example because many of you, all of us, we know already this formula from our school days. So given two data points in an n-dimensional Euclidean space, so how to find the distance between them, right? For example, if it is a three-dimensional space, two data points in three-dimensional space, one is 735 and another data point is 326, then how to find the distance between two data points? So all of you know two-dimensional coordinates, xy coordinates. So that is the physical distance between any two locations. So if x and y coordinate of any two places is given, you can always compute the direct distance between them, right? You see the Google map many times, you give two places and you can see the distances. So these coordinates are given, so already we know how to find the distance between them. This is called Euclidean distance measure. So here sorry. So here these two data points x and y, their distance can be computed. x1 minus y1 square, 7 minus 3 square, plus x2 minus y2 square, plus x3 minus y3 square whole root over, which is 18 root over is equals to 2.426. So you know, if this Euclidean distance between any two data points is more, let's say you find the distance between any other data points P1 and P2 and the distance is, let's say, 10.5. So you know that those two data points are far away from each other as compared to x and y. Therefore, those two data points are highly dissimilar as compared to x and y. So this kind of proximity measures are called dissimilarity measure, right? So opposite of it is called similarity measure. So there exist many dissimilarity measures and similarity measures in the literature. Again, that depends upon what kind of data you are going to use. So if the data is numerical, this is one of the very popular measure. Minkowski measure is also for the numerical data, and if the data is categorical, then there are other measures which can be used, so that you can study if you are more interested in that. So the such kind of measures exist. Another popular measure is cosine similarity, the angle between any two cos angle between any two data points. So then next factor which influence the clustering is called quality of clustering. So there is usually a separate quality function that measures the goodness of a cluster. So how to define which two clusters are good, which two clusters are not good, which two clusters are more coherent to each other, which two clusters are not, right? Which two clusters are more separated from each other. So how do we know this? So it is hard to define similar enough or good enough. The answer is typically highly subjective in nature. So we do not have a definite algorithm, definite technique by which you can measure that the clusters formed or the clusters that are within are good or bad. Still, since we have to implement, we have to find the clusters, so there should be some ways to quantify those similarity or dissimilarity or the goodness of the clustering. So we have many of such techniques exist. So some of such techniques are sum of squared errors, rand index, adjusted rand index, Loti coefficient, etc. So I will not cover this, I will not go deeper into it. When you use the cluster analysis technique, you can go through the formulas. So I will concentrate on the one part of the clustering aspect, so that is the different kind of clustering algorithms. So there are many techniques exist. So one such technique is called partition based clustering. So all of you might have heard about K-means algorithm. Hopefully you know, because it's a very popular clustering technique. Very popular because it is very fast, simple to code. Code is available in the Python library. So here we choose different cluster centers. Suppose this is some data points are given, and you choose let's say 5 different cluster centers and assign the data points to their near cluster center. For example, this yellow point is nearer to its cluster center. This data point is nearer to this cluster center as compared to this or this, right? Therefore this data points belongs to the cluster having this as a cluster center. Similarly, this data point is more closer to this cluster center as compared to this or this or this. Therefore this data points belongs to this cluster having this point as the cluster center. So this kind of clustering techniques are called partitional clustering techniques. So you have K-means algorithm, K-measured algorithms, those are very popular partitioning based clustering techniques. Then another very popular clustering technique is hierarchical based clustering. Those are very old clustering techniques known. Right, in the hierarchical based clustering techniques, you find the set of data points, then you make them into groups. So this is 2 points are grouped, here it is shown. So then again in the next iteration you form a hierarchy of groups like this. So this kind of tree is formed. This tree is called dendrogram. At any point of time you can cut the dendrogram and can form the number of clusters. So if I cut the dendrogram here, so I'll have 2 different clusters, those are formed. So one is this and another is this, right? So there are 2 kind of hierarchical clustering. One is called divisive top-down approach and one is called bottom-up approach. So if you are interested, you can go through the literature, because today's talk is not about hierarchical clustering, so I'll skip this. Then another very popular clustering technique is density based clustering. So many of you might have heard about DB scan, right? So this is a very old clustering technique, highly popular and highly used clustering technique is called DB-scan. So it based on the density. If you look at this data given in picture C, you see that these are from the core area of data, so called dense area of the data, and they are separated by sparse regions. So if you look at these data points, so these data points are examples of sparse area which separates the dense area, right? So and then some data points which are far away from the data points, the core area, are called outliers. For example, these two are considered outliers. So based on the density of the data points, so you have to identify different regions based on their density distribution. So if they are highly dense regions, so you can identify them as denser regions, and some regions are sparser regions, and some data points are outliers. So this is a technique which is very useful if the data contains noise and outliers. Other algorithms may not be able to identify the noise and outliers. They can influence the clustering, but density based clustering, the main advantage is they can identify the noise and outliers, right? So they do not influence the clustering algorithm, and after that, once the outlier data points are removed, for example, you can remove these two data points and can identify two clusters here. So those two clusters are one is this, and the other one is this, right? So they are very helpful to identify arbitrary shape clusters. So here the shape is different. So many such algorithms exist nowadays in the literature. You can go through it if you are more interested. So today's talk is about graph based clustering. Is there any question? I don't know.
There are two questions raised by participants. One
So
is
the questions now.
uh, whenever you feel. They are in the chat.
Okay, let us take the question. So what is, how K-means will perform for big data? Is it suitable for big data? So big means, the question is how big, right? So you have to define that. What is the size? The K-means algorithm, the advantage of K-means algorithm is, it is the size, the running time of the algorithm is, you can note down, the running time of K-means algorithm is n. N is number of data points into D. D is the dimension of the data. K is the number of clusters into I. I is the number of iterations, right? So the influencing factor here is n anyway will be there. Dimension, if it is higher dimension, it will influence. Number of clusters is more, then it will also consume more times, and I is the number of iterations till the K-means algorithm terminates or converges, right? So this is the running time of the algorithm. If your data is huge, then probably use in suppose millions number of points, then there are two factors actually when you say about the size of the data. When you say the large data, so one is the size, second is which computer you are going to use, right? So if you are thinking about running on your own laptop or desktop, then even probably 1 million point you cannot able to run on your laptop or desktop. But if you have a good server, then yes, 1 million points you can able to run. So if you are super computer, probably 1 billion number of data points you can able to run. So there are two factors. One is, this is most of the cases a linear time algorithm, right? And if you have a good computing system, then depending upon your computing system, you have to look if linear time algorithms can still run on your computer. So that you have to look at. So there is no definite answer to say that yes, it's good or it is bad. But if it is still huge, you cannot able to run, then look at the algorithms which use data summarization techniques, right? They first summarize the data, they choose some of the data points which represents many other data points, right? And then apply the clustering on only on the summarized data rather than the whole data. Those are very scalable. Those can be easily clusterable in many of the data sets. What are the other questions? Which type of clustering is used to capture the data for satellite images? Exactly, I do not know what kind of data is images, but there is not a definite answer. Probably I will not say which algorithm is exactly good. If your data points image contains noises, then you go for, let's say, k-means may not be very suitable. Then you can probably go for density based clustering, right? So I am not very sure about this. Which type of clustering is used in Alzheimer's disease project? Actually, I don't know, because unless you know the data, I cannot able to say which clustering is good, right? So that depends, as I had told you, how many clusters are there, what kind of groups are there, right? Whether the groups contains arbitrary shape clusters, what is the dimension of the data. If it is highly dimensional data, let's say 1000 dimension number of features, or the dimension is huge, then many algorithms fails there, right? Then the size of the data is huge, many algorithms also failure. So I cannot able to answer directly that which kind of algorithms will be useful unless I see your data. I have not applied algorithms on this particular kind of data. I have applied on gene expression data. I have seen that graph algorithms are very helpful on that, right? And many real life data I have also seen, but not exactly this kind of disease data. I am sorry for that. What is n and d in k means? So n is the number of objects in the data set, d is the dimension in the data, dimension, number of features, right? So that is called d, number of columns. Number of rows is the number of objects, d is the dimension or number of features, k is the number of clusters, I is the number of iterations. Okay? I think there are previous lectures available in the YouTube. I had given only one lecture on k-means. You can go through that. Asutosh, you can share with them about k-means algorithm. If they have interest, you can go through it. There are a lot of details discussed. Lot of things were discussed on that lecture. So you can go through it if you are interested. Okay? So then today's talk actually is about graph clustering. Why? Because we have been seeing that graph clustering has a lot of potential. They can able to identify arbitrary shape clusters. They can able to identify different clusters of different sizes. You can easily compute the neighborhood information, which points are closer to each other, which points are not. So in today's lecture, we'll see much more details about them. So how the graph clustering works, right? So graph clustering works on this. If you look at this, so this is input data set which is given in the first one. Then in the graph clustering, first thing is you first construct a graph. So this is called the graph representation of this data. So I'll give a mathematical definition of a graph if you do not know. So if you look at this, you will see that there are exactly the same number of data points which are present here in the data. Here it's a two-dimensional data. The number of features are 2, the x-axis value and y-axis values. And you see there are some connection between them, right? So the connections are called edges between them, how far they are each other. So if you look at these two data points, this one and this one, they are neighbors to each other. They are far away from each other. and if you consider this data points and this data points in the two-dimensional plane, if you look at, they are more closer to each other, right? So there exists an edge between them. Then what we do is, so this is called a graph. So once this graph is formed, so next question will be how to partition them, into different clusters. So if you say there are 3 clusters exist in this data based on their separation value, so we'll see that probably I'll find this is a connected component, this is another component of the graph, and this is one more component of the graph. So somehow if you can cut these edges and you can form disconnected components. So these 3 are disconnected components. These data points are more closer to each other. So we'll say that these 3 are the connected components, and then if you look at the actual data points, then they represent, here is the actually 3 clusters. So these are the basic steps in the graph clustering. So one is first giving the data. Graph clustering means you take the data in the first step. In the first step, you model the data as a graph, and once you have a data as a graph, then find the densely connected components of the graph. So once you identify the densely connected components, so those represents the actual clusters. Now the next question obviously will be, given the data points, we know in the n-dimensional space it is actually a matrix. It's a two-dimensional matrix. Rows represents the data points and columns represents the feature vectors. Then how do we convert a n-dimensional data into a graph? So the next question will be, what exactly is a graph? So the mathematical description of a graph is a triplet representing V, E and W. V is non-empty set of vertices, E is set of edges between a pair of vertices, and W is their distance between them, or their weight between them. For example, graphs can be of 2 types: broadly directed and undirected. For example, if there is a direction between data point y to x, then we have a direction here. Let's say x is a teacher, and all these data points here represents the students. So if you draw an edge between a student to teacher, so there is an edge between y to x. If x is a teacher of y, then this will be a directed graph, right? So from a student you have a edge to his or her teacher. So here this one more example. Let's say teacher, student. If x is a teacher, y is a student, there exists an edge between them. So you can model that as a graph. An undirected graph, if there exists a path between x and y, let's say there exists a road network between x and y, so you have a edge between them. So let's say it's a two-way road exists, right? It's a railway network. So that is, railway network is one example of undirected graph, right? In the same railway track, both the directions the train can travel. So this is one example of undirected graph. So these are very basic terminologies in the graphs. Number of edges incident on it is called the degree of a node. For example, degree of this node x is how many nodes are connected to this. So 1, so this is an edge between this. 2, there is an edge between this node x and this. 3, and this, there is an edge between this and this. 4, right? So the degree of this node x is 4. However, this, if it is a directed graph, we say in degree and out degree. We will not use in degree and out degree. Let us just concentrate on degree of a undirected graph. Henceforth, we will only consider this undirected graphs. So some of the more terminologies that will be used in the graph clustering is walk in a graph between nodes x and y. So we say there is something called a walk. There exists a walk between two nodes here. Suppose you start from this node, visit to this, visit to this, then again visit to this, again visit to this, again visit to this, again you can visit this and this. So this is one example of a walk. So if you look at this in every way, every time you visit, you will see that suppose you are visiting from this to this node, from this to this to this node, then this to this node, right? So between every two conjugative vertices, if there exists an edge, you can visit one node to other, otherwise you cannot visit. So that is one example of a walk. So what is a path? If no vertex is repeated, that is called a path. For example, if you start a path from here, if you visit this to this node, then this to this node, then this to this node, it's a path. But if you visit this to this again, so there is a repetition of the vertex x. So this is a walk, but this is not a path, right? In the path is a walk where no vertex is repeated. So we'll be using those in our the path between them, because it establishes a connectivity. So in the graph clustering, what we do is, many times you find if two vertices are connected, right? If there exists a connection between them, is this vertex and this vertex connected? Yes, there is a connection, means there exists a path between them, that means they are connected. If you start from a vertex, you have a path to reach another place, then such a case is called there exists a path, means two vertices are connected. So if every vertex in a graph is connected to each other, then we say the graph is a connected graph. For example, this is one example of a connected graph. You take any two pair of vertices, this vertex and this vertex, you find there exists a path. What is that path? This to this and this to this. There exist many paths, but if there exists at least one such path, then we say these vertices are connected to each other. And if between every pair of vertices there exists a path, then we say the graph is a connected graph. So this is one of the example of a connected graph. This is one of the example of a connected graph. Okay? And the question is, next is, how do we represent the graph, right? How do we represent? Because as a computer science student, or if you want to do any kind of machine learning algorithms, so you have to code it. So in order to code, first thing is you must store the graph, right? For visual perception, it is easy to visualize a graph, but for sake of computing, visual things is not going to help us. We should have a data structure to store the graph and process the graph, where we can able to identify which are the vertices, how many vertices are in the graph, what are the edges exist in the graph, what is the degree of each node, and so on. So there are basically two data structures which are very popular data structures. So one is called adjacency matrix and other one is called adjacency list. So adjacency matrix is a n cross n matrix. It's a n cross n matrix. So n is the number of data points. So in this graph, if you have 6 number of nodes, so if you have a matrix 6 cross 6 matrix, you can always represent this graph. So this is a unweighted graph. So say this rows and columns, this is 6 number of nodes and 6 number of columns, and if there exists an edge between any pair of vertices, you can include 1, otherwise you can include a 0 in the matrix. So A, there exists no edge between them, therefore this value is 0. A to B, there exists an edge, therefore this value is 1. let's say C to D to C, there D to C there exists an edge between them, therefore this value is 1. Similarly C to D there exists an edge, therefore this value is 1. Otherwise, if there exists no edge, let's say between B and F there exists no edge between them, so if you look at B and F, this value is 0. Similarly B and F, this value is also 0. So this is basically a symmetric matrix where Aij value is same as Aj value, right? Because if there exists an edge between Aij, I and J node, then there also exists an edge between J and ith node. Therefore, it's a symmetric matrix where the diagonal elements are zeros and upper triangular matrix or lower triangular matrix are same. So another way of representing any graph is called adjacency list. So what is adjacency list? So in the adjacency list, you can have a linked list of all its adjacent nodes. So any two nodes are called adjacent to each other if there exists an edge between them. So B to E there exists an edge. Therefore we say these two nodes are adjacent to each other. So which nodes are adjacent to node A? Node B is adjacent, node E is also adjacent, whereas A and D are not adjacent to each other. Therefore, here the list of A contains two nodes B and E. These two nodes are adjacent to node A. Similarly, node B, E and A, these two nodes are adjacent to each other. For example, if you take this node, let's say F. So for F, E and D and C, these three nodes are adjacent nodes of F. Therefore, in the F's adjacency list, you have three nodes C, D and E. So this is a single, let's say singly linked list, right? So if you look at here irrespective of how many nodes are adjacent nodes, this is every row of every row contains exactly n number of values. Similarly, any column also contains n number of values. Whereas this is a more compact way of representing the data, where if you see what is the degree of node A, so you can just count its linked list. So it contains two nodes only, therefore the degree of the node is A. If I say what is the degree of the node E, by looking at this you see there are three nodes in its linked list, so you say 3 is the degree of the node F. But if I ask you, given this adjacency matrix, what is the degree of the node C? So you have to look at all the rows elements, right? So all the n items you have to read to say the degree of the node C is 2. So that is one of the main advantage of having a linear list as compared to a adjacency matrix. Here space requirement is more, n cross n, whereas this space requirement is, this is the number of edges exist in this graph, right? Every edge is represented twice. For example, AB node is represented once here as AB and once here in BA. So 2E is the times every node is represented twice, plus B is the number of vertices, right? So this is the size of this linear linked list. So we say it is order of B plus E. So if number of edges is very less, then this is a better way of representing the matrix. Next is if it is a graph can be of two types. One can be unweighted graph, other can be weighted graph. So what is a weighted graph? In the weighted graph, every edge has a weight. For example, distance between two places, right? If you open the Google map, you find you are at place B, you want to visit, let's say F, and then you look at the Google map, suppose you have to go through E, then it will show you the distance as 1 kilometer from B to E and 5 kilometer from E to F. so it will show you 6 kilometer, right? So that is called one example of a weighted graph. So if it is a weighted graph, then also the same data structure can be used to store the weighted graph. One is adjacency matrix. So instead of simple zeros ones, you can now store the weight values, right? The distance values in the matrix. For example, between A and B distance is 2, therefore you store 2. Between A and E the distance is 8, so you store the value 8. Between D and F the distance is 3, so D and F the distance is 3, so you store 3 here. Similarly, in the linked list, say a singly linked list, so now instead of the node B, only B, you can also store its weight. So the linked list can be, this is the A's linked list, so it can have B weight 2, then it can have another E and weight 8. So this kind of linked list can be formed easily. All of you might have do this in your first semester BTech undergraduate courses. So suppose given any data, how to form the graphs, right? So distance function can be used to find the distance between any two data points. So one of the, this is taken, this is a graph of a drug network taken from this link given here. You can search the link. I have taken the graph from this link. So this is subgraph of a drug network. So suppose you are finding the similarity between any two drugs, right? There are many kind of drugs. So this similarity can be induced. What kind of gene expressions are induced when you take the drug, you take a medicine, then the molecular structures of the drug, their chemical composition of the drugs, right? Sets of side effects of the drugs, right? Set of targets of the drugs, right? So if you find them, then draw the edges between them, find the similarity between them, then this kind of graphs can be formed. Then find the form, find which kind of drugs are similar to each other, right? Which kind of medicines are similar to each other, so that you can identify this graph. So any data can be modeled as a graph where the nodes or the vertices are the actual data points and the edge between them represents the true similarity or dissimilarity between them. This is one more example of one of my students, PhD students research paper. So this paper is first approximate minimum spanning tree based clustering algorithm published in Neurocomputing. So this is the paper, and this shows the citation of the paper, how this paper is cited by different authors, right? So this paper is cited by Zhong in 2010, and then this paper is again cited by this author in 2011, 2018. So there exists an age between this paper and this paper and this paper. Then this paper is cited by again Jyoti in 2015, and then this is again cited by this this paper cited this paper in 2018, and then this paper again is cited by this author in 2016. So this is the citation network of a paper, right? So this again I have taken from this link just to show how different kind of data can be represented as a graph. So this is one example. I'm sorry. So this kind of data can be represented as a graph where every node is a paper, research paper, and if they are cited, one paper cited the other, there exists an edge between them. So this kind of network can be formed. Then if you want to find out which papers are very close to each other, similar in nature, suppose you want to study something which is related to graph clustering, then how to identify all such papers which are very close to graph clustering. Suppose if I want to find out which which kind of papers are related to this war going on, so that I can also continue doing research, I can explore what are new things going on, then I can look at this graph and identify the papers. by looking at the clusters. So what is graph clustering? So given an undirected graph BEW, partition the graph into k subgraphs on the basis of their edge structure. So each subgraph in a graph can be a cluster. So in its loosest sense, a graph cluster is a connected component, right? In a connected component, every two vertices are connected to each other. In its stricter sense, it's a maximal clique of a graph. What is a clique? So we say a graph is a clique. Every pair of vertices there exists an edge. So this is a clique of three vertices. So if it is another 4, then this is one example of a clique of size 4, because every two vertices there exists an edge. So this kind of graph structures we need to explore. So we'll say those are the clusters. So first question will be how to model the data in the form of a graph. So given the data, first question will be we have to model them as a graph. How to model? So given the input data set X of d-dimensional data, the graph G is VEW can be constructed by considering the data points as vertices and the dissimilarity or similarity between them representing the edges, edge weights, right? So this is one example of two-dimensional data points. Then what you do is you construct a graph between them. So if distance between them is given, so this is one example of an undirected graph, unweighted graph. So you can also consider a weighted graph where between every pair of points there exists an edge. So the question actually will be which way we can, given any two data points, you can, let's say, apply simply the Euclidean distance. You can find the Euclidean distance between them. Any question? This type of graph can help in literature survey. Yes, sir. Previous slide, please. That slide I'll request Asutosh to share. Probably he has shared the slides already. So no more question. Okay. So how to consider this, how to model this graph, right? So there are many techniques exist. So one such technique which is very popular is k nearest neighborhood graph. So if you have already done machine learning courses, so KNN classifier is a very popular classifier, right? So how do we construct a graph? First thing is how to find the similarity of k nearest points. So how to identify the k nearest neighbors? So here, given the data, we say between data points there exists an edge in the graph if any point V is among the k nearest neighbors of U. In this example, this k value is 2, so it's a two neighborhood graph. For example, if you look at this point, so which are its two neighbors? Two nearest neighbors. So obviously one nearest neighbor is this and other nearest neighbor is this point. Therefore, from this data you have two edges. So if I take this point, let's say, so it's which two data points are the two nearest neighbors. So obviously this and these two data points are the nearest neighbors of this. Therefore, this is the way we draw the nearest neighbor graph. Whereas if you take this another data points, let's say, so if you take this data point, so which two data points are nearest neighbors of this data? So obviously not this, neither this. So it is this and this. Therefore you find there exists edge between this point and this point. So these 2 points are the nearest neighbors. So therefore it's a, you say U to V there exists an edge. So there may not exist an edge always from V to U, right? So there exists an edge between this to this, right? But there doesn't exist an edge between this vertex to this vertex because they are not shared, they are not mutual neighbors of each other, right? Therefore, we say this is a directed graph. So this is one example of k value is 2. K means how many nearest neighbors. So we can have 3 neighbors, right? Then similarly every vertex has 3 nearest neighbors which are drawn. For example, if you look at this vertex 1, 2, 3, these 3 are the nearest neighbors. Then again k value is 4. So we have 4 nearest neighbors of every vertex. So if you look at this vertex, its nearest neighbors are 1, 2, 3 and 4. So this way you can consider the graph, but as I have told you, this is a directed graph. It's a very popular way of constructing the graph. Most of the literatures, if you study in graphs, so you find k nearest neighbors mentioned in them. So following strategies can be used to make a NNN. Please previous slide KNN. Okay. So it says the following strategies can be used to make KNN as a undirected graph. So how to make this as a undirected KNN for k value 4. So if UV belongs to E, then add the edge UV also. So if there exists an edge between any two nodes, let's say U to V. So if there exists an edge U to V, then you also add an edge V to U. So if UV is an edge, means VU should also be an edge. Now if you look at as compared to the previous graph, you find in case of k equals to 4, so this node and this node are now neighbors. So this node has other 4 neighbors which are nearer 1, 2, 3 and 4. Whereas there exists an edge between these two because this is the neighbor of this node, therefore there exists an edge between them, undirected edge. So very popular clustering, the way of constructing graph is called mutual KNN. So in the mutual KNN graph, add the edge connecting two nodes U and V only if both U and V are k nearest neighbors of each other. For example, now k value is 4. So if you look at the k value as 4, so you will find that let us consider this node. Let us consider this node here and here. So if you find a mutual neighbor, so this node is not a mutual neighbor of this because this node, let's say 1, this node is 2. So 2 is the nearest neighbor of 1, fourth nearest neighbor of 1, but so 2 is let us mark this as 1 or mark this node as 2. So here 1 to 2 there exists an edge because 2 is the nearest neighbor of the node 1, but 1 is not the fourth nearest neighbor of 2. Whereas in this graph, so we need to have we have an edge between two nodes if both 1 and 2 are nearest neighbors of each other. So in this graph, 2 is nearest neighbor of 1, but 1 is not the fourth nearest neighbor of 2, therefore there exists no edge between 1 to 2. Whereas here this edge exists because this, let's say, is 3. So node 1 and 3 are neighbors of each other. So in this graph, 1 is nearest neighbor of 3 and 3 is also the nearest neighbor of 1. Therefore there exists an edge between them. So if you compare these two graphs, what you can observe here is the number of edges in this graph is much lesser than number of edges in this graph, right? Because you include one edge between any two vertices provided they are mutual neighbors of each other. Therefore this graph has less number of edges. Though less number of edges, this graph also correctly projects represents the structure of the data. What is the structure of the original data? these two are outliers. So this is almost one cluster and this one is another cluster. So if you look at this, these data points are closely related, these two data points are closely related, and so on. Therefore, therefore those structure of the data is correctly captured. So this is one of the way of constructing the graph. So another way, very popular technique to construct the graph is called epsilon neighborhood graph. So what is epsilon neighborhood graph, or scanning radius based neighborhood graph? So in all those edges belongs to the graph that are having weights less than the scanning radius. So first you fix a scanning radius. Let's say scanning radius is 1.1, and you find the distance between every pair of data points. So if the distance between any two data points is within the epsilon radius less than or equals to 1.1, then you draw an edge between them. For example, between these two data points there exists no edge because their distance is greater than 1.1. And if you consider these two data points, there exists an edge because their distance between them is less than or equals to 1.1. Similarly, if you look at, you increase, it is 1.1, let's say we increase it to 1.3. So again more edges will be added because the distance is growing. Further, if you increase epsilon value to 1.7 here, so if you see that the number of edges are increasing. So it was 1.1, very less number of edges. 1.3, edges are increasing. 1.7, more edges are getting added. 2.1, even these two buttocks are now connected to each other, and it's a highly dense graph, right? So this controls the density of the graph, that how the data points are closely related to each other, right? The more edges will be added if you take higher epsilon values. So this way, given the data, you can always construct different types of graphs. Okay? So KNN graph, mutual KNN graph, or epsilon neighborhood graphs. Then another commonly used graph modeling is called fully connected graph. So the similarity between the 2 points decided by a Gaussian kernel function. So we say any two data points s, xi, xj has a value, it is e to the power minus the Euclidean distance between xi, xj, the square of that divided by 2 sigma square, where sigma is a controlling sparsity, right? So here this example is when you take the sigma value as 0.024, this kind of graphs are constructed. So you are increasing the value of sigma 0.34, 0.4, so you have different kind of graphs constructed. Then many of you might have heard about minimum spanning tree based minimum spanning tree. Given a graph, you can always construct a tree. So what is a tree? A tree is a connected acyclic graph. The tree contains all the vertices, and it is connected between every pair of data points. There exists a path, and there exists no cycle in the graph. So a minimum spanning tree or minimum weight spanning tree is a subset of the edges of a connected edge weighted undirected graph that connects all the vertices together without any cycle and with the minimum possible total edge weights. So given this unweighted graph, if you look at, right, so these are the edge weights given. For example, between these two vertices, edge weight is 18. This between these two vertices, edge weight is 10, and so on. So if you given this graph, can you find a tree in the graph where when you add all the edge weights in the tree, that value should be minimum? So I say this is one of the minimum spanning tree. Why it is called a spanning tree? Because all the vertices are covered here, right? This tree contains all the vertices in the graph. First criteria. Second criteria is this tree doesn't have a cycle in it, right? So here there is no cycle in the graph. If you look at the thick edges, right, thick edges, and then there is no cycle here. And third criteria, if you just take the sum of all these thick edge weights, for example 3 plus 2 plus 2 plus 8 plus 8 plus 7 plus 4 plus 1 and plus 3. So this is the minimum weight possible. If you construct any other tree containing all the vertices and then add their edge weights, then you will find that the edge weights cannot be lesser than this. So that therefore this tree is called a spanning tree. Then the next question will be, given a graph, how to find the spanning trees of a graph, right? So there are many techniques exist. If you have studied the data structures and algorithm course in your second semester BTech or first semester BTech course, you must have studied data structures and algorithm. So the very popular algorithms are Borbukka's algorithm, Kruskal's and Prim's. So briefly I'll just discuss any one of the algorithm, and if you are more interested you can go through the literature. You can find them in the any algorithm textbook. So let us discuss about Prim's algorithm. This algorithm was developed by Clay Prims. So this algorithm is very simple. We assume that there are n number of disjoint trees, and will every iteration will add one disjoint tree to our tree. Will grow the tree and will stop when our tree contains all the vertices in the graph. So this is a weighted graph. So this Prim's algorithm starts from any of the arbitrary vertex. Let's say this vertex I will start, and from this vertex find any node which is whose edge weight is the minimum. So out of 11, 13 and 8 we will find that this is the minimum. So you include this. So in the next iteration we have a connected edge between V and this node, right? So this is a tree, and all other nodes are single node trees. So every iteration we will keep on adding. We are growing our tree, so we'll add one node into the tree. Then in the next iteration find the minimum edge weight which connects our tree with any of the node. So if you look at this now carefully, we will see this edge is connected, this also can connect another edge, this also can connect another vertex, and this edges can connect. So out of this 6 edges we find this edge weights is minimum. So next iteration we will include this edge, and now our new tree has these 3 nodes. So again look at similarly, if you grow the tree, next iteration out of all the connected edges, this 13, 7, 12, 40, 20, 7, 6, you will find that this is the minimum. So you connect this edge, right? So this is the next edge. Next time this is added, next iteration this new node is added. So till now how many nodes are added? 1, 2, 3, 4, 5 and 6. How many remaining nodes are there? 1, 2 and 3. So next iteration which node will be added? Any guess? So it is this node. Then next iteration, any guess which node will be added? So this node is added, right? So only one node remain, which is this. This has to be added. So from this and this, if you find this is the smallest one, so you add this edge. So if you look at this, this is called the minimum spanning tree. So all these nodes are connected. What is the tree? So the tree that is formed is this, right? So if you look at this connectivity, so there is no cycle, all the vertices are covered, and if you take the sum of all these edge weights, 13 plus 18 plus 2 plus 6 plus 1 plus 3 plus 10 plus 9, and you will never find another tree, spanning tree, whose edge weights will be lesser than or equals to this sum. Therefore this is one example of a minimum spanning tree. So this minimum spanning trees also can be used to construct or model the data as a graph, right? So if this is a graph, we will find that this minimum spanning tree that we have formed can be a graph, right? Can be a graph. It contains lesser number of edges. So this is the data. So given the graph, you can always construct a minimum spanning tree of the graph. So if you one round of the graph, if you apply minimum spanning tree, you see in this data that this one graph is formed, right? So this graph contains all the vertices are connected now. The graph contains no cycle and the edge weights is minimum, right? So what if you apply, if you remove all these edges from the original graph, right, and then apply the remaining graph, if the graph is not disconnected, then you can again apply one more round of minimum spanning tree. So if you apply one more round of the minimum spanning tree, many new edges will be added, and clearly this graph is no more a spanning tree. It is no more a tree because this graph now contains cycles. However, if you look at this graph, the graph models the original data very nicely because these two data are far away from other data sets, other data points, and these data are more close to each other, and these data points are very close to each other. So this is a good modeling of the data. So when you apply the clustering, we will most likely identify these two as clusters, or they belongs to the single cluster, and then there can be there can be as a cot somewhere here. So this set of data points in one cluster, and this will be in another cluster. So this way also we can model the data as clusters. So it is shown here, k equals to 1, one round of MST, k equals to 2, second round of MST, k equals to 4, 4 rounds of MST edges are added, k equals to 5, 5 rounds of MST edges are added. Then what is the use of this? So MST is a very popular technique to find the clusters. So till now what we have discussed is how to find the clusters in the data, how to model the data, right? So given the data, we can form the clusters using many different we can form the graph using many different techniques. So one technique is KNN graph. Another technique is epsilon neighborhood graph. Another technique is a fully connected graph, and then last that we have seen is the minimum spanning trees. Now we will move towards, once the graph is formed, how to find the actual clusters in the data, given the data now is actually a graph, right? So how to find the best connected components, closely connected components in the graph. So give me 1 minute, a sip of water.
Excuse me, sir. Sir, excuse me.
Hello.
Yes, sir. Can we find minimum spanning tree of the previous complex graph in the previous slide? That type of graph.
What? Can you repeat your question?
Can we find the minimum spanning tree of that complex type of graph?
Any graph is given, right? If the graph is
So
connected,
manually it is difficult, but is there any software to find out directly to MST of this complex graph?
why do you say it is difficult?
Because there are many nodes are there, no? Because like many connectivities are there, no? Manually it is impossible, as I think.
We will not do manually. So we have algorithms. So you can
Prim's
write.
algorithm.
Yes.
So Prim's algorithm also there is a manually we generally used to solve, no?
No. This is for demonstration only. So we take smaller graphs to give the demo to the students sometimes. But so that doesn't mean that we cannot write usually in undergraduate the first year students write the codes in their data structure course to do all this. So if you say, I can share the code also, this minimum spanning tree code, so we have available given the data. Even this k rounds of minimum spanning tree can be constructed. So we have Python codes, we have MATLAB codes. So nobody does it manually. In machine learning, if
Okay,
you do
okay,
manually, then what is the point? Let the machine to learn, not the
okay,
humans, right?
okay. Really, really. Thank
So
you,
we
sir.
have the code. Every time we
So
will
please,
write the
please,
code.
please, sir,
Okay.
please, we want that code also.
Okay,
Please
we'll
share the
share.
code. Okay, thank you.
So what we do here is, given this graph, can we apply how to find these closely connected, densely connected components, right, which are very close to each other? So we can again apply the minimum spanning tree of the graph to find the k minus k number of clusters, right? So this is a very simple graph based clustering algorithm. So given this data, first one, if you look at 1 minute. So if you look at this one, this is our input data, two-dimensional data. And if you look at this, most likely most of you agree that this contains 5 number of cluster. One is this concentric circles, two concentric circles, and here there are 3 clusters. So total 5 number of clusters. So first point is how to form the graph. So if you apply the KNN graph, here we have applied the mutual KNN graph, which is shown here in the green color. So it's a graph, right? So this graph is constructed. So third step of the algorithm is, given this graph, this is a connected graph, so you construct a minimum spanning tree of the graph. Okay? So the spanning tree of the graph, if there are n nodes, the spanning tree of the graph always contains n minus 1 edges. So if you add n edges, the graph is no more a tree, it is a cycle. For example, if you take any graph, so let's say 3 nodes, so 1 2, so it's a 1 2 3 nodes. So if it is two edges, then it is not a cycle. The moment you add one more node, it is a cycle. Definitely cycle will be formed. So if it is a 4 node graph and you have 4 edges, minimum 4 edges, then the graph is definitely cycle, right? So it is not a tree. So if the graph contains n number of vertices, so the minimum spanning tree will have will have exactly n minus 1 edges. If n edges, the graph is no more a cycle. So it is a graph, right? From this graph we compute the minimum spanning tree. Let us say we apply the Prim's or Kruskal algorithm to compute, right? So if you look at this, these are the edges, right? These are the edges shown here, and these are the edges connected. So this is one edge, and this graph points are also connected between them. There exists an edge, there exists an edge here, there exists an edge here. Okay? So this is a minimum spanning tree that is constructed of this graph. So given the data, first construct a graph, maybe epsilon neighborhood graph, maybe KNN graph. From this graph, construct the minimum spanning tree, and from this minimum spanning tree, so if you want to form 5 clusters, then identify the 5 longest edges from the graph. So look at this graph carefully, you will find that this edge is one of the longest edges. So this is probably the second longest edge, this is probably the third longest edge, and this is probably the fourth longest edge. Now the theorem says, if there is a tree, and from a tree if you remove any edge, then the graph will be a disconnected graph. So suppose this is one example of a tree. So if you have removed this tree, so this will make the tree disconnected, right? So if I remove again, so again this is a tree and this is another tree. So if you remove any tree, any node from the graph, then we will show that you will see that the graph, any edge from the graph, from the tree, the graph will be a disconnected graph. So if I remove this, If I remove, if I remove this node, this edge, this edge, this edge, and this edge, so four disconnected components are formed. Clearly, it is visible. One is this component, then the other one is you can clearly see here. Other one is this connected component. Third connected component is this. Fourth connected component is this, and this one. So I have four connected components. Each connected component is now a cluster for me. So here if you look, all the clusters are colored using different colors so that you can easily visualize it. So these are the five set of clusters formed. So this is one of the very simple clustering techniques. Is there any question for plotting network can be used? Are they cyclic? Which one is cyclic? Sir, we should start from lowest weight. Sir, is there any software to plot MST of this type of graph? Yes, you have codes available to plus cluster, right? One out of many resources available for MST code in MATLAB. So many codes are available. What is, are they cyclic? Third, how to define running time complexity. So this third means what? Cyclic तो नहीं होगा ना. जब स्पैनिंग ट्री है, ट्री जब बोला जाता है, ट्री में कोई साइकिल नहीं होता है. Otherwise that is not called a that is not called a tree. So tree is connected as cyclic graph. Connected graph having no cycle is called a tree. When the tree contains all the vertices of the graph, that is called a spanning tree. And when the sum of the edge weights of the spanning tree is minimum, such a graph is called a minimum spanning tree. So these are the three definitions. So hopefully if many of you are studying it first time, you may not able to grasp it immediately. Please go through the lecture when it is uploaded, and still if you have any queries, you can always ask me. I am available. You can drop me a mail. I can clear your doubts. So somebody asks, what is the time complexity? The time complexity is a good question. So time complexity of this graph construction so the time complexity of this graph construction is, this is suppose n number of data points. So if you apply, let's say KNN graph, minimum time required is n square, right? Because between every pair of points you find an edge, right? So if you apply epsilon neighborhood, you apply KNN neighborhood, you apply fully connected graph. So the time complexity of the graph is order of n square, because between every pair of vertices you find a distance, right? So once the graph is constructed, find the minimum spanning tree. So what is the complexity of the minimum spanning tree? So if the graph size is n square, so the running time of minimum spanning tree is also n square. So if the graph size is the number of edges is e, then the size of this minimum spanning tree is v plus e log e, right? You apply a Prince, you apply Kruskal or whatever. So since this graph size is n square, so computing this minimum spanning tree also take order of n square time. Okay? So this is, hope it clears everything. Once it is done, so there are only n number of edges in the graph now, n minus 1 edges in the graph. So out of n minus 1 edges, you find the k minus 1 longest edges in the graph, right? So here find the 5 longest edges in the graph, 1, 2, 3, 4 longest edges. So that can be done in order of k times only. So in order of a k times, you can form the connected components of the graph. So once connected components are this graph is disconnected, next question will be how to find the connected components. Is there any answer given this graph? Because still this is a graph. So how to find the connected components in the graph? Do you know any algorithm to find the connected components? So if any of you know already BFS, the breadth first search or DFS, you can always apply them to find the connected components. You can recursively apply the breadth first search algorithm. So suppose on any node in this graph you apply BFS. Let's say here you start the BFS. So the breadth first search will find all the nodes. Then again you apply BFS at some other node. Let's say some node here. So it will find this all the nodes which are connected. Then you apply again BFS as some other node, let's say here. So you find the connected components, all the connected components. Then you apply, let's say, some node here, it will find this connected components, and finally this. So you apply BFS 5 times till you find all the connected components, so that you find all the connected components. So how much time BFS takes? So if you have studied the BFS algorithm in the hopefully all of you are computer science students. I do not actually know your background, so I am sorry for that. So these are the fundamentals in computer science. So I assumed that all of you know these graph terminologies, like what is a graph, nodes, vertices in the graph, then BFS, DFS. So I assumed that all of you know almost. So if you do not know, please go through it once after the end of the lecture, so that when you rewind the lecture, you will find that you understand the lectures properly. So when you apply the BFS and somebody asks the running time, again this will take V plus E times if the graph is represented as a adjacency list, and order of V square time if the graph is represented as a adjacency matrix. So this takes order of V square time, and this takes again order of V square time, and this takes order of K times, and this steps takes again order of V square time. Therefore the clustering takes order of V square times, where V is the number of vertices in the graph. So this is one more example of the same data. So what you can observe here is, this one is a very highly dense graph. Dense means number of edges are more. Sparse graph means number of vertices are less. So if we look at this graph now, the same data, however the number of edges are very less now as compared to the second figure. The number of edges here is very less, right? So this is called a sparse graph construction technique. Many my PhD students are actually working here on how to reduce the size of the graph, so that the computational complexity of clustering algorithm can be improved. So instead of order of V square time or order of n square time, basically, can we able to reduce the time complexity of the graph clustering further, so that we can speed up the clustering process. How this graph plotted? There are plotting techniques in the MATLAB as well as in the Python course. So unfortunately there is no lab sessions for this clustering session where I can show you the demo. So if you say I'll share this coding, so I'll ask my students to share the coding with all of you, so that you can also plot the graph and do the clustering. So this sparse graph can be constructed, right? So this is a very good research going on currently, that given the data, how to construct the sparse graph out of it in less time, not in order of n square time. Though we have different techniques, KNN, we have epsilon neighborhood, we have the minimum spanning tree based cluster, the sparse graphs techniques, but all of them takes minimum order of n square time. So we have shown that we can still able to reduce the time by avoiding construction of edges. So just I'll give the gist of all this research that we people are doing. So if you look at these two vertices here and here, so this is one of the longest edges in the graph. So why do we at all need this edge? We do not need, that is not going to help us in the clustering. So can we avoid this edge during the construction? Yes, we can do this, and currently my students are able to reduce the time from v square n square to order of n to the power 3/2. So we have a order of root 10 factor improvement over the time complexity of this kind of clustering algorithms. So what I want to tell you here in this slide is, given this, you can construct a sparse graph, and given this sparse graph you can reduce the time complexity of constructing this. So we can construct this sparse graph in order of n to the power 3 by 2, means n to the power 1.5, right? From this, now you can construct this minimum spanning tree from n to the power 1.5 log n. This time you can able to construct this minimum spanning tree. So this can be done in order of k time, and then this can be found out in order of b plus c time, right? So in linear, so the overall complexity of the algorithm can be reduced to this one instead of order of n square. So we have shown that the quality is still retaining, right? So this kind of clustering algorithms you can explore. This is very efficient. This can explore the clusters, the data set containing arbitrary shape clusters, right? For example, this is one example of arbitrary shape clusters, cluster within clusters, the variation between densities, right? So one cluster size is huge, other cluster size is very less. So all this kind of clusters, this is very helpful. Asutosh, can I continue?
Yes, sir.
Okay. So one more clustering technique which is very popular, which many people might have heard about, is called spectral clustering, which is again one of the graph based clustering technique. So what is exactly spectral clustering? So in the spectral clustering, given the input data, you can always find the similarity graph. So given this data, these techniques already we have seen. So you construct a similarity graph, let's say KNN graph. From the KNN graph, we compute a matrix called Laplacian matrix, and from the Laplacian matrix, we compute the smallest eigenvectors. I will give the definition of eigenvectors, don't worry. Then from the eigenvectors, then we can analyze the data and find the clusters. So this is very popular. This can work on many kind of data. So let us look at step by step. So in the graph cut, actually what we are doing, we are finding the cut of the graph. So there are different cut properties of the graph. Given a graph, this is a weighted graph. So the min cut is a problem which says that selecting two sets of subset A and B such that you can minimize the sum of edge weights between them. So if you look at this example, let's say this is one set and this is one set. So which set of edges connects this one, let's say x, and this one is y. Which set of edges connect x and y vertices? So these two edges, right, the red color edges, so the edge weights is 0.4 and 0.5. So what is the sum of this edge weights? 0.5 and 0.4 is 0.9. So if you cut this way, then the min cut value, this cut AB value is actually 0.9. Now let us see another example of the same graph. So here I have this same graph again given. Now let us make it two different partitions, one containing all the vertices and the other containing only one vertex. Let's say this vertex set is x and this vertex set is y. So now the question is, what is the value of this cut AB? So let's say this is my A and this set is B. So which edges connects the set of edges in set of vertices in A to set of vertices in B? So this red color edges are the only two edges. So it is 3.5 is the distance and 0.4 is the distance. So if you take the sum, this cut value is 0.7. So the min cut is minimize this quantity, right? So if you similarly explore all possible cuts, in these two cuts, if you consider, you find this is a better cut, right? This is the minimum value, 0.7 is lesser than 0.9, So this cut is a better cut. However, if you look at it carefully, you will see that this cut in the prospect of clustering, this min cut is a better cut. First one is a better cut because you probably will say that this one is one cluster and this is another cluster. And here, if you cut this way, so this one is one cluster and this single node is another cluster. So min cut is obviously not the best way for clustering, finding the clusters. So in order to overcome this issue, we have other clustering technique, other cuts. One is called ratio cut. So what is the ratio cut? So ratio cut says approximately both the clusters should have same number of vertices, right? So if that is the case, then the cut is better. So if you look at this in the min cut, we have now added 1 upon number of nodes in A, set A, and 1 upon number of nodes in set B. So in the same example, cut value was with this cut AB is 0.9, and what is this 1 upon A? 1 upon A is how many nodes in A? So this is A and this is B. So 1, 2, 3, 4, 1 upon 4. And what is B? 3 nodes, 1, 2, 3. So 1 upon 3. So now this value is 0.525 instead of 0.9. So in case of min cut, the value was 0.9, whereas in case of ratio cut, now the value reduces to 0.525. Now again consider this example. So we will consider this example. So this is one cut and this is another one. So if you now consider the value was 0.7, 0.3 plus 0.4, 0.7. Now what is 1 upon A? So this set A contains 1, 2, 3, 4, 5, 6 nodes. So 1 upon 6. And what is the value of B? The value of B is only, as the number of elements in B is only 1. So this is 1. So 1 upon 6 plus 1 upon 2, 1 is 0.82. Now if you compare both T, which one is minimum? So this one is minimum, right? So now this ratio cut is able to rectify the problem, because even if you have a very bad cut, right, like this and this, but still this is a ratio cut is able to identify this is a better cut than this one, right? So another very popular cut is called normalized cut. So in the normalized cut, instead of number of elements A and number of elements in B, so we have volume of A and volume of B. What is volume of B? So volume of A is, suppose this is your A and this is your B. Volume of A is all the edge sum within this set A and all the edges sum within the set B. So take all these sums. So this is, if you look at this volume of A, so this set has 4 nodes. So what is the volume? This degree sum of A is 0.7 plus 0.8 plus 0.4 is 1.9. Degree sum of U3. So U3 is degree sum of U3 is 0.9 plus 0.9 plus 0.7, which is 2.5. Degree sum of U4 is 0.9, 0.8, 0.8, 0.5, which is 3. And similarly U7 is 1.8 and 0.9 and 0.8 is 0.17, so 9.1. So now you can put the value here and you can find the normalized cut. However, these two cuts are very good on this different cuts. This is one of the way of cut and this is another way of the cut. This cut contains 4 and 3 vertices. This cut contains 5. All 6 and 1 vertices only. So here min cut value 0.9, 0.7. So if you apply min cut, this cut will be preferred. If you apply ratio cut, this value is minimum, so this cut will be preferred. Even if you apply normalized cut, this is a much better representation, right? See, it is huge now. The difference is 1.05 versus 0.308. So this is a better way of cut. However, though normalized cut and ratio cut can give you the clusters, But the issue with ratio cut and normalized cut is this: they are NP hard problems, right? They are hard problems. We do not have polynomial time algorithms known to find normalized cut and ratio cut of any graph. Therefore, we cannot able to apply in real life applications because they take exponential time. So what are the solutions? So we design approximation algorithms. So how to approximate them? We apply the relaxation algorithms using eigenanalysis, right? So what we do is, we have graph, we construct on normalized graph Laplacian. So on normalized graph Laplacian matrix is D is the degree matrix and W is the weight matrix. Let us go here and see the example. Given this data, this is a data, this is a similarity graph, okay? So here these edges are given, it's a unweighted graph, and this is the adjacency matrix W. So if there exists an edge between any two vertices, the value is 1. If there exists no edge, the value is 0. For example, 6, 3, there exists an edge. Therefore, if you apply 6 and 3, this value is 1. Between 6 and 2, let's say there exists no edge between them. Therefore, 6 and 2, this value is 0. So this is called adjacency matrix. We have already seen from the beginning of the lecture. Then find the degree matrix of every node. So if you look at the this value 0, 0th node, what is the degree of this node 0? So degree of this node is 3. How many adjacency nodes? 1, 2 and 3. So then a degree of the node, let's say 1. What is the degree of the node 5? So 1, 2, 3. So degree of the node 5 is again 3, right? So if you look at this, degree matrix is only a diagonal matrix. All other values are zeros because we are only storing the degree of every node. Okay? So now we have matrix W, which is the weight matrix, and we have adjacency matrix, and we have the degree matrix D. So what we want to now compute with this? We will compute the Laplacian of this. So what is the Laplacian matrix L? So Laplacian matrix L is degree matrix minus W matrix. So it's a matrix subtraction. D is a matrix, diagonal matrix, and W is a matrix. So now you subtract between, component wise subtraction between D and W. So it is 3 minus 0, it is 3, 0 minus 1, it is minus 1, then 0 minus 0 is 0. Similarly, let's say 3 minus minus 4 is this 4, 0, 3 minus 0, it is this is 4, so it is 3, then it is 0, let's say 0, and this value is 1. 0 minus 1 is minus 1, 0 minus 1 is again minus 1, and so on. So this computation is easy, simple matrix subtraction. So once this L is computed, next question will be compute the eigenvalues of this matrix, Laplacian matrix L. So I do not know how many of you already know eigenvalues. You might have studied the eigenvalues in your school days, or you might have forgotten it. If you remember, given any square matrix X, so we say V is a vector which is called eigenvector of a matrix A if A V equals to lambda V, right? Here A is any square matrix, V is a vector, lambda is any scalar. So we say V is lambda is the eigenvalue and V is the corresponding eigenvector. So how do we compute the eigenvectors and eigenvalues? From our school days, you might have solved this characteristic equation A minus lambda I the determinant of this is 0. So you solve this inequality for the values of lambda, and then when you find the values of the lambda, if it is a n cross n matrix, there are n values for a 2 cross 2 matrix, you will find 2 lambda values. For a 3 cross 3 matrix, you will find 3 lambda values, and so on. So those are called the eigenvalues of matrix A. Once you find the eigenvalues, then you can put in this equation and solve the equation for each eigenvalue to find the eigenvector of V. So these are the techniques you might have studied in our school days, right? Mainly in the intermediate, we have already, if you have a mathematics course, you must have done it. So if you are a science student, you must have done it. If your background is not science, probably you do not know. So assume that we have this Laplacian, and we compute the eigenvectors. So if you want to find two clusters, so find the two smallest eigenvectors. So for this particular matrix, we have computed here using a program to find the eigenvectors. So this is one of the eigenvectors. Clearly see, this is a 7 cross 7 matrix. Therefore the size of this vector is 7, right? Sorry, this is a 8 cross 8 matrix, 0 to 7. So therefore the size of this vector is 8. Similarly, this is the second eigenvector, so its size is again 1 cross 8, 8 cross 1. So now these two are the vectors. Okay? Now we stack them in this way, one after the other. So this is my first eigenvector, this is the second eigenvector. So now if you have two clusters, now this is my new data point. So what initially I started with this graph. Okay? So this was the graph. What I have reached right now is this. Now I have only a two-dimensional matrix, and this two-dimensional matrix is my data, new data, right? Only two-dimensional. So initially your data might be a d-dimensional data, let's say 1000-dimensional data, but now you are able to reduce the data into a two-dimensional data. So now this two-dimensional data, so I can find which kind of clusters can be formed. So look at this carefully, you can easily understand from now on. So if you clearly look at this x and y axis, I am going to plot it now. So if you look at it carefully, please look at this. Let's say this is my x coordinate and this is my y coordinate. And if I want to plot, what kind of plot I will form? So all the x-axis values are same, minus 0.35. So if I plot, this is my minus 0.35. So the data somewhere will be like this. So this is my y coordinate value is bit different, but x coordinate value remains same. Therefore, all the data points will be in a single vertical line parallel to y axis, right? Y equals to minus 0.35. So this is where I have plotted. Now initially we had 8 points, but now if you see, probably when I have plotted them, we'll see that hey, there are only 4 points. Where are the other 4 points? But if you look at this carefully, that's why I'm telling you, please look at this data carefully. You will see that these data points, these 3 data points have exactly same x and y coordinates. Similarly, these 2 data points have exactly x and y same coordinate. Sorry, this along with this one. Okay? So these 3 data points have exactly same x and y coordinate. So this data point is different and this data point is different. So when I plot, these 3 data points goes to exactly one particular point in the xy coordinate. This one goes to this one becomes my second point. These 3 data points will go to the third point in the coordinate. So this one is the fourth point, different, fourth. So therefore, here you see only 4 data points are visible because 3 data points are merged here and 2 data points are merged here, right? So I have only 4 data points. Now once I have all these values, can I able to apply k-means on this? So any post clustering algorithm I can apply on this. So you see how beautifully we have managed to transform the data into eigenspace. So I started with this data, right? So this was my original data. They were scattered around. I was unable to probably find which two set of data points are closer to each other. Now if you look at the transformed space here, so now see clearly, if you ask somebody, he can say that these two are the clusters. There are two clusters and these two are the clusters. Now you apply any post clustering algorithm to find these two clusters. So finally these are the two clusters formed, right? So for clearly see here, so this four data points, one is here and one is here, the original data points are plotted. So this kind of clusters are formed. So let us see one more example on a bit complicated data. So this is one data. First step of spectral is model the data as a graph. So this is KNN graph for mutual KNN for k equals to 3. So after that, next step is find the Laplacian matrix. So once Laplacian is formed, find the eigenvectors. So since this data I know number of clusters are 2, so I find the two smallest eigenvectors. So here the heat map is given. So this is my eigenvector 1. Clearly you will see from the heat map that all the values are exactly same. So if this is my coordinate, so this is all the points will lie on a single line parallel to y-axis, and the second eigenvalues varies, right? The second components vary, eigenvector components vary. Therefore you see they all lie on a single line. They all lie on a single line parallel to y-axis. Okay, so therefore if you look at this, okay, show all the data points, then apply k-means on this, providing k as 2. So this transformed data points are clustered in this. So now you map the original data points. So this is the clusters which is formed by the spectral clustering. One more interesting data is this all these data sets are called synthetic data sets because it's the two-dimensional data sets which are generated, right? So this is again contains arbitrary shapes. It says its shape is different, this shape is different, this is sphericals, right? And one cluster size is very big, other cluster size is small, right? Density distribution of this is pretty more, and this density distribution is also more. So this is this kind of data. Apply spectral compute, since we know, suppose that four number of this contains of 4 clusters, 1 2 3 and 4. So we compute 4 eigenvalues of the Laplacian matrix. This is plotted here, and then it clearly distinguishes the clusters, right? So this set of data points belongs to one cluster, this set of data points 1, and this set of data points 1 and 1. So this way these 4 clusters are formed, right? So this is all about the spectral clustering. It's a emerging area of research. Lot of scope is there to do future research. I hope you have understands the basics of graph clustering, and it will help you to explore much more. So maybe these are the places from where I have taken all the documents, lecture notes for chapter 7, introduction to data mining. Then this is downloaded from this link is provided. Then data mining book, concept and techniques, 3rd edition. This is a very interesting book. Then some documents are given from these e-sources, and then some are minimum spanning tree based clustering, and many of the figures were shown through the actual programs. Okay, thank you. So maybe if you have few queries I can take, otherwise you can stop.
So do the participants have any query? Okay, so I think it is all. Yeah, please.
Yeah, I'm audible, sir.
Yes,
Yes,
yes.
yes, yes.
Go ahead.
Yeah, sir, what sort of challenges are possible in this spectral clustering, sir?
One of the challenge that people have been working or it is going on is spectral clustering running time is actually order of n cube, right? N cube is huge. So how to reduce that? So that can be further reduced provided the size of the spectral graph can be reduced, right? So how to reduce the size of the spectral graph? So if the graph is just very sparse graph, let's say order of n number of edges only, then in the spectral clustering you can apply the spectral clustering and spectral clustering become faster. So this is one of the interesting research area, that how to construct the graph. The graph can retain or preserve the topological distribution of data points. So if we can form such graphs which actually represents the true nature, neighborhood nature of the data, then and the size of the graph is less and the construction time of the graph is also less, let's say assume order of n, then the spectral clustering will take less amount of time, right? Then the next question will be, once you have all these graphs, then how efficiently you can construct the eigenvalues, because it depends upon the eigenvalues, right? So we compute this eigenvalues using QR algorithm, which is again if not a very fast algorithm. So how to reduce the time of that? The next interesting question is, uh, given the graph, how efficiently we can compute the eigenvalues, and next is how to find the best value of this k, right? So in eigen computation, or here in spectral clustering, we provide k as a input. So if k is not known, so people use the eigen gap, we say eigen gap analysis. So how efficiently we can automatically detect the number of clusters?
Okay, sir. Thank you, sir.
Are there any more queries? Yes, the material will be shared to you all. It is the lectures on the drive, and other materials will also be shared.